We jump to section 2.4. Section 2.4 is now finding derivatives using chain rule. Well, when do we need chain rule? Chain rule comes into play when we have those composite functions. Well, what's a composite function? Well, if we have the good old days of, some of us like to call it fog, the fog thing, well, what's that really mean? Well, that's really composing the f function with the g of x function, taking the second one and putting it inside of the first one. So when we have a function that looks like this, and we want to take the derivative, we would need to use this chain rule. So if we need to go to use this chain rule, again, what we're looking for is a function inside of another function. So what we really do with chain rule is we take the derivative of the outside times the derivative of the inside is really what it comes down to. Derivative of the outside times the derivative of the inside. Well, what does that mean? Well, I'm going to take this problem number 1 and I'm going to rewrite it. Now, I know I'm going to need a lot more room, so I'm going to zoom this in just to make a little bit more room for myself. So let's see. I'm going to start by rewriting this function. 2x plus 1, we've got a constant in the numerator. Now, some people look at that and go, Mr. Perkins, shouldn't we use quotient rule? And the answer would be yes, you certainly could, but you don't need to, because if you look at it, what's the derivative of the numerator eventually going to be? It's going to be 0. So if you did do quotient rule, when it comes time to do the derivative of the top, that term is effectively going to disappear. So if you notice in a problem like this that immediately either the derivative of the numerator or the denominator is a constant, or the derivative is going to be 0, then you don't need to use that hard rule, and you can actually rewrite it and make things a little easier on yourself. So I'm going to rewrite this as 2x plus 1 raised to the negative first power. So when I look at this now that is a composite function. That is a 2x plus 1 inside of something being raised to the negative first power. So I'm going to treat the 2x plus 1 as my red function. So I've got the red one inside the black one. So we go to take the derivative. So our dy over dx, I'm going to start by taking the derivative of the black function. What's the derivative of something raised to the negative first power? Well, that's negative 1 times that something to the negative second. There's the derivative of the outside function. Well, now I'm going to multiply that by the derivative of the inside function. What's the derivative of the inside function? 2. Well, but that doesn't make sense, Mr. Perkins, because that's a little bit blank. Okay, well, what was inside that black function originally? 2x plus 1 was? Well, it's still going to be inside the derivative. So the derivative of the outside is negative 1 times something to the negative second. The derivative of the inside is 2. We're going to multiply those two things together. When we multiply those two things together, now we can go ahead and we can clean it up. So if we go and we clean this up, let's see. So we've got a negative 2 in the numerator over a 2x plus 1 quantity squared. And again, remember, never, ever, 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 ever multiply out denominators. It just doesn't, it's no good. Problem number 2. Now, number 2 is a little bit more straightforward, because I can see right here that I have a 3x to the 4th minus 5. That's my red function on the inside, and that is all being cubed. So if that's being cubed, we've got a composite function. Outside is something cubed, inside is this red thing. So let's do our derivative. So our dy over dx, derivative of the outside function would be 3 times that something squared. Derivative of the inside function would be a 12x cubed. Well, now what was inside the original function, inside that cube? The 3x to the 4th minus 5 was, and now we're ready to go. I'm hoping that you're not going to break the rules of algebra and try to distribute that 3 into the quantity squared, because exponent rules supersede multiplication. But I can take the 3 and the 12x cubed and multiply them together, and if I do that, how about 36x cubed times the quantity 3x to the 4th minus 5 being squared. Now, you certainly could multiply all that out. You could multiply out the binomial and then distribute the 36x cubed. I wouldn't advise it, because what we're going to find as we get past the skill of taking the derivative and get to the application of taking the derivative, you're going to like that form a lot better. Problem number 3. Again, I'm going to rewrite it, because what I'm looking at right now I don't especially like. I've got, let's take this x squared minus 1 and let's raise it to the 2/3 power, so that something to the 2/3 power is now my outside function, and my inside function is an x squared minus 1. So derivative of the outside, let's take care of that first. 2/3 quantity, subtract 1 from the power, negative 1/3. What's the derivative of the inside function? Or the inside function is 2x. And now to complete everything, what was inside before is x squared minus 1. So let's make sure it's still inside of that black function. Now we clean it up. If we clean it up, looks like our numerator is going to be a 4x, and our denominator is going to be a 3, and an x squared minus 1 to the positive 1/3 power. Last but not least, last one is the most complex of the four, of course, because now here's what I see. I've got a numerator that's derivative is not going to be 0, so I'm going to actually have to do quotient rule here. So before I do that, I'm going to write this thing without the radical. So x squared plus 4 to the 1/3. Well, taking inventory, we're going to have a product rule, or a quotient rule here, sorry. But when it comes time to take the derivative of the denominator, I see x squared plus 4 inside of something to the 1/3. We're going to need chain rule when it comes time to do the derivative of the denominator. So here we go. So f prime of x. Low x squared. So let's do the red blue thing that we've done. So numerator is red, denominator is blue. So we're going to start with low x squared plus 4 to the 1/3 times the derivative of the top times the high, which would be 1, or d high would be 1, less the high function, which is the x. Now this is where things get a little bit exciting, because now it comes time to do the d low. I've got x squared plus 4 inside of something to the 1/3 power. So we're going to do this chain rule thing. So the derivative of something to the 1/3 power would be 1/3 of that something to the negative 2/3 power. And then we've got to go, okay, well, what's that something? Well, that x squared plus 4 is inside of something to the 1/3. What's the derivative of the x squared plus 4? 2x. And then don't forget to put your x squared plus 4 back in. So this, all of this disaster right here, is the derivative of the bottom, the blue function. And now finishing off your quotient rule, we've got an x squared plus 4 to the 1/3 being squared. So that's going to raise this to the 2/3 on the bottom. All right, well, this is terrible. This is awful. How am I going to simplify this? Well, let's rewrite it so it looks like it's supposed to. What we really have is we've got x squared plus 4 to the 1/3 minus, how about 2x squared over 3 quantity x squared plus 4 to the 2/3 over x squared plus 4 to the 2/3. So some people are going to say, well, just cancel the x squared plus 4 to the 2/3. Well, that doesn't work. We've got fractions inside of fractions. If we have fractions inside of fractions, the fastest way to get rid of them, we've talked about, is let's multiply the top and the bottom by what's causing the problem. Well, what's causing the problem? Looks like that 3 and the x squared plus 4 to the 2/3 is. If I do that and I distribute this orange thing, first term is going to become x squared plus 4 to the 1/3 times x squared plus 4 to the 2/3. That's just an x squared plus 4 multiplied by a 3. Minus, if you distribute the orange thing to that second term in the numerator, we're going to cancel the denominators out. It'll leave us at 2x squared. Oh, so much nicer. And on the bottom, when you multiply that orange thing times the pink thing, you're going to get a 3. And you're going to get an x squared plus 4. What's the new power on it? Well, 2/3 plus 2/3 would be 4/3. Can I cancel the 3's? No, because I can't get one out of all the terms. The 2x squared doesn't have one. Can I cancel the x squared plus 4's? No, again, because the 2x squared doesn't have one. So my only choice is to clean up the numerator and put my like terms together. So if I clean up the numerator, let's see, 3x squared plus 12 minus 2x squared over this denominator. Whoops, not 2/3, 4/3. And if we finish this off, 3x squared minus 2x squared is an x squared plus 12 over a 3, and an x squared plus 4 to the 4/3. Wow, that's rough. That is really rough. Why is it so rough? Well, to be totally honest with you, on problem number 4, you've got one of the most complex setups that you could possibly have, because in this original problem, you have a fraction, a black fraction, with a red x on the top and a blue x squared plus 4 to the 1/3 on the bottom. Quotient rule is hard enough for us right now, but now in this particular problem, nestled within that denominator is an x squared plus 4. So you have a chain rule inside of a quotient rule. So we took care of that. We did chain rule first. When it came time to do the we did quotient rule first. When it came time to do the derivative of the bottom, we did the chain rule. That's where the green came from. And then we had nasty algebra to try to clean up after that. So this will not be the last time you run into this sort of thing. So take note. Last problem, we've got trig. And now when we look at trig, here's the thing. Trig is not that hard to deal with, but it's set up differently. So what I see here is this f of x function in problem number 5. There's a 3x plus 2 function that appears to be inside of, that you're taking the cosine of. So if we look at it that way, then my outside function, when I go to take my derivative, well, my derivative here, I guess I got, sorry about the space. When I go to take my derivative, my f prime of x, I'm going to start by taking the derivative of the outside function, which is 5 cosine of x. Well, what's the derivative of 5 cosine? Well, that would be the opposite of 5 sine. And then what's the derivative of 3x plus 2? Well, the derivative of 3x plus 2 is 3. What was inside the cosine before? 3x plus 2. So the same idea. You've got an outside function and an inside function. The derivative of the outside function is negative 5 sine of something. The derivative of the inside function is 3. Put the outside function, put the outside function back the way that it was before. My derivative, negative 15 sine of 3x plus 2. Trig can get to be a little bit confusing, but if we treat it the same way that we do algebra, derivative of the outside times the derivative of the inside, it's really not that bad.